you take a database of aligned face photographs, so the faces are roughly positioned in the same spot. And then really every photograph is just a digital grid of pixels, which are numbers. So we can do math as if they were matrices or a 2D array or whatever makes you feel comfortable. And so we can take the average of every single pixel, and that gives us the mean face, the average face, not like rude face. That looks kind of like an empty human. So then if you go down to number 2, right, so like that's the average. So then in the second column here, number 3, we can take each face and subtract off the mean. So the difference from the average face. So what makes this face special, right? Then we can use something called the singular value decomposition, which is a powerful tool from linear algebra, if any of you took that. But essentially, it's going to take the most important values of our matrix, which in this case is a photo, and it's going to build out for us eigenfaces, is what we call them. And so these eigenfaces, you can actually add them up back together to create one of the original faces. And it takes a lot less data than storing every photo's original. And so it's really fast to compare to every image, which is what we're going to do facial recognition here. And you'll see below, like that woman's face is being reconstructed. That's just using more and more eigenfaces to try to recreate the original image. So we take a target image. So this is, now we have our whole database set up with all these eigenfaces. We can take a target image and we can shift it by the mean, which we already have stored, and build it out of our eigenfaces using linear algebra, and then compare that to all the other faces in the data set. And that comparison is really fast because we're using these eigenfaces. It's just comparing to what's highlighted as the difference between each face. And so we find the closest one. And if we get close enough, maybe we stop because we don't want to actually search through all of them. And so you can see here my code had taken the target image and it returned the same person, but we had a few different faces of his. So it was close enough that it stopped, but it didn't find zero difference. It found almost zero difference. So most of the time on this face data set, it actually returns the same person and sometimes even the same photo every time. And it's just doing this by comparing the distance between photos, the distance being a little different than what you're thinking of in 2 dimensions.
Can I ask a question? We got the time?
Yeah.
Yeah, 1 minute.
What's the big O time complexity of step 6?
Of step 6, taking the target image, shifting it by the mean, building it out of our eigenfaces to compare it to the other faces in the data set. Big O where n is what?
Where n is the size of the database.
The size of the database. Okay, so then ignoring the different, however many pixels there are in each photo, it's going to be big O n squared log n.
Cool. Thanks.
So it's not how your phone unlocks.
I was going to say, dang.
But it's the simplest approach. Like you can code, if you understand the math, then you can code it up in less than an hour.
So.
I have a quick question. Underneath step 5, there's that lady, but she's not in any of the original images. Is that significant or?
No, the actual database I was using has way more than those 6.
Okay.
Those 6.
Cool.